Welcome to The Explainer. Today, we're going to jump into a scientific moment from 1995 that basically questioned everything we thought we knew about putting man-made materials, specifically silicones, into the human body. So, back in the mid-90s, this question kicked off a huge scientific debate. For decades, the assumption was that silicones were inert, that they just sit there and do nothing. But then a whole wave of new evidence started to pop up that challenged that fundamental belief. So what do? Well, the National Institutes of Health got everybody in a room for a workshop. The point wasn't to find some magic answer, but to just get all the data out on the table and argue about it. As they said in the notes afterward, this was science happening in real time. Messy, controversial, and all. All right, so to really get what all the fuss was about, we've got to go back to basics. What exactly is silicone, and where does it even come from? Well, the story starts with the element silicon. And this stuff is everywhere. I mean, you combine it with oxygen, and you get silica, which is just sand and quartz. And that makes up a wild 75% of the entire Earth's crust. Now, if you look at the periodic table, silicon is right under carbon. So you might think, hey, maybe it's just like a stand-in for carbon. But nope, not at all. The atoms are bigger, the bonds are different, and those tiny little differences at the atomic level create huge changes in how it behaves. It's its own thing, for sure, not just carbon's understudy. So how do we get from, sand to the silicone we use in products? It's basically a three-step industrial recipe. First, you cook the sand down to get pure silicon. Then you mix that with other chemicals to make these little building blocks. And finally, you just snap all those blocks together into long chains. And voila, you get silicone, a completely man-made polymer. The most common kind, PDMS, has this really cool repeating silicon-oxygen backbone. And here's the magic. Just by playing with how long those chains are and how you connect them, you can make almost anything. Running liquids, thick gels, even solid rubbery stuff. Okay, so we've got this material made from sand and chemistry. The billion-dollar question is, what happens when you put it inside a living, breathing person for, years and years at a time? And a lot of the science back then focused on medical implants. It makes sense, right? I mean, they're a perfect case study for long-term exposure. So you've got a device like this one with a solid outer shell and a soft silicone gel packed inside. But here's where things get really interesting. The big realization was that this thing isn't just a static blob. It's not a sealed container. Stuff could be happening. And scientists were looking at two main things: tiny molecules getting out and the surface of the implant actually breaking down over time. So that first process, they called it gel bleed. The gel inside isn't just one pure thing. It's a cocktail of different sized molecules. And what they found was that the really, really tiny ones could actually sneak their way right through the supposedly solid outer shell, just slowly seeping out over time. The second thing is called hydrolysis. Basically, our bodies are wet environments, right? And the source material showed that over years and years, that water can actually start to break the chemical bonds right on the surface of the silicone. And get this, the prediction was that this could change a huge chunk of the surface, maybe 25 to 30%, in just a decade or so. Okay, so why does that matter? Well, this breakdown creates these new chemical groups on the surface. And here's the kicker. These are the exact same groups that make natural silica, sand, biologically reactive. So the whole theory was, maybe this process was turning a supposedly inert implant into something that could actually start a conversation with our body's cells. And that, right there, is the heart of the whole mystery. If this material isn't just sitting there quietly, if it's changing and leaking, then what in the world does our immune system think about all this? And boom, take a look at this. This picture is incredible. It's actual tissue from a person taken from right beside an implant. Those little bubbles you see inside the cells, scientists confirmed it. That's silicone. It had bled out and was then literally gobbled up by our immune system's cleanup crew, these cells called macrophages. But were the cells just storing it, or was something else going on? Well, in the lab, they took it to the next level. They put these macrophage cells in a dish with silicone, and what they saw was a total game changer. The silicone was actually being broken down. This was huge. It meant the body wasn't just cleaning up a mess. It might have been actively trying to, digest this foreign material. Okay, so this interaction is clearly happening. And that raised a whole new question. Could the silicone be doing more than just being there? Could it actually be, stirring the pot and making the immune system overreact to other things?
There's a scientific term for this, an adjuvant effect. An adjuvant is basically like a hype man for your immune system. It doesn't cause the reaction itself, but it amps up the response to something else it sees at the same time. So naturally, scientists wanted to know, could silicone be an adjuvant? So they ran this key experiment on rats. They gave them a standard protein. Now look at this chart. When they gave the protein with silicone oil, nothing much happened. A tiny blip. But when they mixed it with silicone gel, whoa, the immune response went through the roof. It was a massive spike, just as powerful as some of the strongest adjuvants they use in the lab.
All right, so you see this in animal studies, and the next logical step is to ask, what about people? It kicked off this huge search for a human signature. The thinking was, if this is really happening in people with implants, there's got to be some kind of clue, some sort of immunological fingerprint in their blood.
And that's exactly what they did. This question led to a whole bunch of studies that started looking at really large groups of women with implants, just hunting for any kind of pattern in their immune systems. And I mean, they collected a ton of data. These charts just give you a little taste. They're showing different antibody levels across more than 4,000 patients. It just goes to show you the massive scale of the effort that went into trying to find that one specific immunological fingerprint.
So when you put all the pieces from that 1995 workshop together, the whole picture started to change. The old idea of silicone as this perfectly harmless inert bystander, that was really starting to crumble. The new data suggested it could break down, it could leak, cells could process it, and it could interact with the immune system in some pretty complicated ways. So looking back at this scientific moment from nearly 30 years ago, it's not really about finding a final, simple answer. Instead, it leaves us with this huge, important question that's maybe even more relevant today. As we keep inventing incredible new materials to put inside our bodies, how do we ever truly understand the long, complicated conversation they're going to have with our biology over an entire lifetime?